Okay, thank you very much for having me. So I'm going to talk to you about new lower bounds for private estimation and the generalized fingerprinting lemma. This is joint work with Gautam Kamath, my advisor, and Vikrant Singhal, who's sitting right there in the room. So the motivation for this work has to do with the tools that we have for proving lower bounds for statistical estimation under approximate differential privacy. So we basically have two tools, the fingerprinting method and the DP analogs of the Lecam and Daswam methods. So in prior work that has employed these techniques, it was necessary to have a product distribution and have a precise functional form for the density for fingerprinting in particular. Like any lower bounds that have been proven using these techniques required these conditions to hold. However, there may be some problems where it's necessary to have correlations for the problem to make sense. And one such problem is covariance estimation. So in such cases, we had gaps between the known upper and lower bounds. And also in some other cases, we had lower bounds, but they were under stricter notions of privacy, like pure differential privacy. So let's talk a bit about the fingerprinting method, which is really going to be the focus of this presentation. So the idea is that we have a distribution which comes from a parametric family, which is parameterized by some theta from some parameter space theta capital. So suppose we're given NIID samples from that distribution and we want to estimate the corresponding theta via an estimator theta hat. So consider this quantity over there. On the one hand, we have the correlation between the output of the estimator and the input samples, and on the other hand, we have the estimation error. So the sum of these two terms has to be lower bounded by a positive number. And the reason for that is that if the first term is small, it means that we're outputting something that is uncorrelated with the input samples. So our estimator is not really taking into account what it's being fed with. So in such conditions, it can't really have low estimation error. So these two quantities cannot be too small at the same time. So we sort of have a correlation accuracy trade-off here. So what I just described is commonly referred to as the fingerprinting lemma. The second thing is that if the estimator theta hat is private, then the correlation term must be upper bounded. We can't have too strong correlation between the output and the input samples. And at the same time, if we assume that our estimator has low error, this implies an upper bound on all of the sum that we have there. So we have an upper bound and a lower bound for this quantity, which ends up implying a lower bound on the sample complexity we need to perform estimation. So in the past, this has been applied to single-dimensional distributions. And when it comes to multi-dimensional distributions, the assumption was that we have independent marginals. So essentially, people applied the one-dimensional results. So what we remarked is that you can actually generalize fingerprinting to exponential families. So what's an exponential family? The idea is that we have a known subset of R to the D, which is the domain of the distribution. And we also have some parameter space, which we assume is a subset of R to the K. So we say that a family of densities is an exponential family if it can be written in that form, where we have functions h, t, and z, which all of them have some kind of meaning within that context, but I'm not really going to describe it for the sake of brevity now. So the exponential families are important because they capture many fundamental distributions one learns in an introductory probability and statistics course, like Gaussians, binary product distribution, the geometric distribution, the exponential distribution, gamma and beta distributions, et cetera, et cetera. So as I said previously, we showed, like, the main technical contribution of our work was that we showed that fingerprinting type arguments can apply to all exponential families. So in our paper, which is an archive, we give a general fingerprinting lemma which works for any exponential family, which means that we may also have correlations between the components of the random vectors generated by the distribution. So using this result, we proved a lower bound for Gaussian covariance estimation under approximate differential privacy, where we say that if we have estimation error smaller than some absolute constant and an epsilon delta differentially private mechanism where epsilon and delta belong in these ranges over there, then in order to have mean squared error upper bounded by alpha squared, we need the number of samples that we draw from our Gaussian to be at least d squared over alpha epsilon. So as I said, the proof uses the generalized fingerprinting lemma, and the improvement compared to prior work is that prior work proved this bound under the constraint of pure differential privacy, not approximately. The second result that we have has to do with estimation of covariance matrices with respect to the spectral norm. So if we assume that our estimation error is upper bounded by roughly 1 over root d, and we have an epsilon delta dp mechanism where epsilon and delta belong in these ranges over there, in order to have the expected error measured with respect to the spectral norm be upper bounded by alpha squared, we need the number of samples to be at least roughly d to the 1.5. So the proof of this theorem is via reduction from Frobenius estimation to spectral estimation and by leveraging the previous result. So there had been similar bounds for worst case distributions from a work of Dwork et al. From 2014. So we proved this not for worst case distributions, but for a Gaussian distribution. And this shows a gap between private and non-private sample complexity of estimation of Gaussian covariances with respect to the spectral norm. Finally, in the paper, we also have a result about mean estimation for heavy-tailed distributions. So suppose that we have a distribution with bounded second moments, and we want to estimate its mean with mean squared error at most alpha squared, where alpha is at most 1. And our estimator is epsilon delta dp, where epsilon delta satisfy that condition over there. In that case, the number of samples we have must be at least d over alpha squared times epsilon. So unlike the previous results, the proof for this statement uses the db-Aswad method of Acharya, Sun, and Zhang from 2021. And our improvement compared to prior work is that previously this bound was known only under pure differential privacy. So after stating our results, I'm going to mention some open problems. The first is to investigate further generalizations of fingerprinting. Maybe we can go beyond exponential families and get something even more general than that. The second is prove the previous theorem, theorem 4, assuming that we have more than the first second moments bounded. The third is to expand upon the results of theorems 2 and 3 for larger values of alpha. In particular, this theorem 3, not 2, sorry. So here we have that alpha is at most 1 over root d. This is a consequence of our reduction-based approach. So we would like that normally to hold for the regime where alpha is smaller than some absolute constant, not just 1 over root d. And the last open problem is to obtain lower bounds that also hold in the high probability regime. Like here, you can see that the guarantee that we have is involves an expectation. So this guarantee can generally be converted also to a lower bound for estimation with a constant probability guarantee. Like say that the probability that our estimation error exceeds alpha is at most, say, 1/10. Like there's a way to go from what we have there to a statement of that form. However, if we want to have arbitrary probability of failure, say beta, in that case, it's not generally immediate how to get such a result. And Yeah, the question is to prove high probability lower bounds and incorporate the probability of failure in the sample complexity. So thank you very much.